All right, we're going to start the next part of Project 2 demonstration, which is this third part right here, which is going to be DSK implementation in C using brute force FIR filtering in C. Part 1, sections 3.4 and 3.41. So section 3.4 is just an overview of how we're going to implement the filters in C. So in the previous video, we talked about MATLAB and simulating these results in MATLAB. And the first approach that we used was not effective for real time, but we developed an alternative method to help that can simulate real time a lot better. So with this design in MATLAB, we buffered the data and performed the dot product, and then use the shift register and shift the values in the register. This design philosophy that we developed in MATLAB, we're now going to implement in C to implement our filter, and that's what section 3.4.1 is going to be about. Oh, and I forgot to mention something real quick. For section 3.4, also talk about some of the differences between MATLAB and C. The main difference between MATLAB and C is that MATLAB will start their indices at 1. So if you see here, we load into index 1, but in C, they start at index 0. So here we have Code Composer, where Code Composer is going to be our C++ coding environment. And I have a couple files open right now. So the main C file isn't actually going to be used very much because the main C file is just in a loop that stalls. And the main operations is going to be controlled by interrupts. So we have this FIR mono interrupt serviceable routine, ISR. So this is where we're going to implement most of our code. So there are a few extra housekeeping pieces of code that are used that came pre-coded to read from the DSP board, but there's also going to be code that we implement ourselves to actually design the filter. And the other file that's important is this header file, this dsp-config.h. So this header file includes the settings for the DSP board. So the main setting that we're going to look at is this sampling rate. So the sampling rate of the DSP board right now on the uncommented line I've said is at 8 kilohertz. I've said it only at 8 kilohertz because we're going to be only using low frequencies. I want to use audible frequencies that aren't too high pitched that can cause headaches. So we're going to mainly be using low frequencies. So I'm going to use a low sampling rate, and we shouldn't run into problems there. All right, so now that we have the settings on this, we have the settings for our DSP board, we're going to talk about our code. So I'm going to implement the moving average filter. It's going to be third order moving average with 4 coefficients. Since it's moving average, the sum of the coefficients is going to be 1 equally divided. So here we have 1 divided by 4, just like in MATLAB, 0.25 for all of these. This x left is going to be our buffer. It's going to buffer our data, and this y left is going to be our output. So if we go through our code, we first store, this method grabs the input and store it in the first index of the buffer. In MATLAB, this was index 1, but in C, it's going to be index 0. We initialize the output to 0, just like in MATLAB. Then we perform this loop. This loop performs the dot product, similar to what was done in MATLAB. And this loop is the same as in MATLAB, where we shift the registers. We shift all the data points over at the register. And then we take this output and output it on the DSP board. So that's all for the code. So now we're going to talk a little bit about what the moving average filter looks like. So in the time domain, the moving average filter looks like a rectangle since all these values are the same at 0.25. So a rectangle in the time domain is going to appear as a sink in the frequency domain. Now the sink was going to have the first null of the sink is going to be what we're interested in. So the first null of the sink we're going to find is going to be at the sampling frequency, which right now is 8 kilohertz, divided by the number of coefficients right here in our moving average. So since there's 4 coefficients, our moving average filter should have its first null at 8 kilohertz divided by 4, which is at 2 kilohertz. So at 2 kilohertz, there'll be a null. So if we run this by running the debug. Yes, we'll terminate the current session, and once this thing is done building, it'll download onto the DSP board. All right, so then we resume. So like I was talking about earlier, since this is this has 4 coefficients, and the sampling frequency is 8K, we're going to do 8K divided 4 is 2K. So the first null is going to appear at 2 kilohertz. Right? So if we take our 2 kilohertz and we run it, you don't get any sound at the output. That's because we're at that null band. We're at that first null. So if we're at the first null here, that means everything less than 2 kilohertz is inside the first lobe. So I can take a 1 kilohertz signal and I can get an output. And I can take any signals less than 2 kilohertz and they'll be in that inner lobe. So now we can experiment a bit with our moving average filter. So let's say we make our moving average filter a little bit bigger. So 7th order filter means that we're going to have 8 coefficients. So it's going to be 1/8 for each of these, 1/8 for each of these coefficients. So now we have 1, 2, 3, 4, 5, 6, 7, 8. We're going to run this new filter again. So we run this filter. So just like before, since we're using 8 kilohertz as our sampling frequency, and we have 8 coefficients in our moving average filter, the first null will appear at 8 kilohertz divided by 8, which is at 1 kilohertz, which is experience our first null at 1 kilohertz. So if I run this, and I go over here, and I go to 1 kilohertz, and I run 1 kilohertz now, notice how we're not getting any sound at the output anymore. And this is because now the first null has been shifted back to 1 kilohertz. But anything less than 1 kilohertz is still going to be in that main lobe. So I can take this 500 hertz signal and I can still get a signal out of it, or I can still get an audible tone out of it. And if I can even go up to 900, you can still get something. It's a bit faint because you're reaching that first null, but it's still audible. So one last try. We could try one a little bit bigger. So 15, we can go up to 0.625, which is 1/16. And we're going to need 16 of these coefficients. So as you can expect, since this is going to be 16, you're going to do the sampling frequency, which is 8K divided by 16, which is going to give you 500. So that means that the first null will now appear at 500 hertz. So if I just copy this, so this should be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Hopefully that's about 16. So we run this, and we should have 16 coefficients. That means 8 kilohertz divided by 16. So the first null is now going to be at 500. And remember, it's a sync, so that means after it hits that first null, it will bounce back up. So even frequencies above 500 will be there, but they'll be attenuated because they won't be part of the main lobe either. So if I run this, and then I run my 500 hertz signal again, you get nothing because now the first null has been shifted over to 500. If I take something less than 500, it'll be in the main lobe. That's 3,000, not 300. Where's 300? 300's in the main lobe. Or I can take something higher than 500, like that 900 or 700 signal. You'll still get a tone because it's not going to zero it out. Instead, it's going to go into the next lobe, which is a lot smaller, so it's going to appear attenuated. So the moving average filter works kind of like a low-pass filter, but it's a sync, not like a rectangle. And so the two main problems with this implementation is that, as you can see here, when the number of coefficients gets large, I have to manually type out all these numbers. So if I run a much higher order filter, because FIR filters can have hundreds, possibly hundreds of taps, then this is going to be a very tedious process to get all these coefficients typed in there. And the second problem are these shift registers. So shift registers are not a very efficient way to move data around. So when you shift, you have to perform an operation to move each data into the next slot in the register. And this can be inefficient. And we want to be efficient with our code because our DSP processor can only perform a certain number of operations before the next sample. So with our DSP configured, I have it set to the lowest sampling frequency, 8 kilohertz. That means it takes 8,000 samples a second. So before the next sample comes in, the DSP board has to calculate the result for the current sample. With lower sampling frequencies, that gives the DSP board more time to calculate the result, so it can perform more calculations. But at higher sampling frequencies, it'll have less time. And so if if we're not efficient with our resources, we can't perform as many calculations because we're wasting them shifting data in the registers. So then we can't perform as many operations per clock cycle at higher frequencies. We'll tackle both of these problems in the other sections. The first problem we're going to tackle is going to be the problem of having to write out all these coefficients. And we'll talk about how to solve this problem later in the next video.